Good morning. Nice to not see you all today. Everyone's so shy they never share their cameras. So we're going to launch into part two of our introduction to ceramics. I'll remind you that you're welcome to post questions in the chat, or you can raise your hand or whatever, and we can try to do it that way. The way that we've done it in the Dropbox is that the original slides go in the Dropbox, which have they are the PowerPoint as prepared, and then I save at the end of the session. I save all the annotations. So there's a second file with a similar file name that says Anno, ANNO at the end for annotation, and all the annotations that I've done on the screen here are captured and they're saved. So the course is incomplete because you can watch the video again, and it will track the annotations as they occur, but you also have a copy of those. So here's where we are today. Let's see. There we go. Okay. So part two, just a recap of what we did yesterday, basically. Okay. Review now. Ceramics have high melting points. They typically are very good electrical insulators. They are typically good thermal insulators with a couple of minor exceptions. Materials that have high thermal conductivity. Most are insulators. They're optically transparent. They tend to have high strength and also be very stiff, meaning high elastic modulus. But they are low toughness, meaning that they're brittle with a couple of exceptions, being partially stabilized zirconia and silicon nitride. They're abrasion resistant, and they have, in general, low thermal expansion coefficients. And the takeaway yesterday was that our testing of industrially created samples supports a hypothesis that the strength controlling defects are linked to the manufacturing process. And by that, I mean two bodies that go through the same process, potentially multiple bodies. One may be higher strength than the other, and that increase in strength is due to a difference in elastic modulus, but the flaw populations for both bodies appear to be the same. That's a big deal because it helps us then identify where to look for a problem if we have a problem in terms of manufacturing. And we propose in general that these flaws are particle agglomerates and that are not eliminated in the existing process. Now, that doesn't mean that you need to go eliminate these agglomerates. The fact is that it may be that it takes a lot longer time in, say, a mill, for example, to eliminate those agglomerates, but it may not be a benefit financially. So where we want to go today is here. I plan to start with powder characterization. And we'll go through the sort of natural discussion about density and surface area, but we're going to spend quite a bit of time on particle size distributions. I will go into ceramic forming processes from a relatively high elevation view, and then we'll discuss cracking and warping. And I think that's probably going to wrap up the day. I have thermal processes at the end of this, drying, calcination, sintering, etc. And ideally, we get to that today. So, okay. So, powder characterization. We know that ceramics are all manufactured with few exceptions starting from powders. Okay. And those powders come to us in a variety of form. If you were a pioneer, for example, moving across the country, you might dig clay out of a hillside and make a pot out of it. Those days are more or less gone. Now raw materials come to us from raw material suppliers. They mine the raw materials of interest. If they're lucky and they're things like clay, they can just put them in water basically, and the particles will deagglomerate and you get slurries. No particle size reduction is necessary. In fact, in those systems, they might remove the coarse particles through a sieve process or through an air flotation process or hydrocyclone or something like that. Examples of that are the paper industry. Other than that, materials that come in have to be ground, and they are ground, and that produces log normal distribution, basically. So we need to characterize those materials because that distribution and the particle size affect our process and it affects packing. Okay, so density we get through a pycnometer method. We'll walk through that. Specific surface area through nitrogen absorption. Important for small particles, not particularly important for coarser particles. And then the particle size distribution, and we'll go through sieving and sedimentation-based measurement devices, or scattering in case of laser, and then powder packing and how powder packing works. The ones at the bottom, the four listed at the bottom, I don't go into today. If there's an interest, we can talk about it. But thermoanalysis is very useful for some powders. If you had aluminum oxide, for example, you might argue that there's no need to do thermal analysis. However, you would be able to detect presence of a hydration layer on the powders, for example, in a high surface area powder through DTA, TGA. If you had a carbonate, of course, it would be useful because you'd see the evolution of CO2. Chemical analysis is quite valuable, but very few people do that in-house. That's done essentially outsourced to a commercial lab, and it is valuable. What we have found over the years is that the consistency in raw material chemistry is remarkably good. And that it's sort of we've worked a lot with raw material suppliers in the past. And it is interesting because the standard joke, I used to always teach this in my class, when you have a problem in your process, what's the first thing that you do? And there's lots of answers. Oh, well, you blah, 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 blah. No, first thing you do is you blame the raw material supplier. And so raw material suppliers are aware of this, and they are quite good. They will keep witness samples. They track the chemistries. They come in, they know the particle size distributions. They know the surface areas typically. And if you come in with a problem, you go, you sent me a material doesn't work. They go, well, it's within your specification. Here's the data on your sample. So although they used to be blamed for everything, now the fact is they're in really good control of all that. X-ray diffraction for mineralogy and SEM is great. We love to look at pictures, nice pictures, but it is of limited benefit in most of these cases. Before we go any farther, though, we have to talk about sampling. So anything that you test in the laboratory or in a quality control lab is making an assumption. And that assumption is that the test specimen is representative. Okay. Oops. Change my. It is representative. Okay. And that means that if I characterize that sample, the properties of that sample are consistent with the whole. So if you had a 50-pound bag of, say, silicon carbide grit, and you took that 50-pound bag and you did a sieve analysis of the material in that bag, you would come back with the particle size distribution. If you take a sample of that material, let's say you take out 100 grams of that 50-pound bag to do particle size distribution, what should happen is that those two pieces of data match. If they don't match, you have a problem, of course, because you're measuring then something that's not representative of the whole, and you're making an assumption that it represents the whole. This is probably the most important step in powder characterization, is to get a representative sample. You say, well, what about the process itself of doing the measurements? I'm not arguing about that, but the fact is, if you measure a sample which is not representative, the information you get is not of value in your process. So all specimens should be either split. Splitting is the preferred method, okay? And splitting, we have three examples over here. This is called coning and quartering up here at the top. And you pour the bag out on typically a big sheet of paper, and then you quarter it, and you take opposite quarters, for example, this quarter and that quarter, you combine it back together, and then you do the process again until you have split down to the sample you need for measuring. So if you had a 50-pound bag, you split it the first time, you get back 25 pounds, and then you get 12 pounds, and then you can do the math, 6, 3, 1.5, until you get down to 100 grams. that takes some time. So they came up with this device. I don't know what the name of it is, but you pour in a bag here of a material, and there's a bar here that you can adjust to change the height of that, and it comes down as a sheet, and it trickles through the material basically, and a small sample comes out this end. Okay, and the rest goes out the back through these holes. Okay, so as it goes back out through these holes, um, you're able to basically, the material gets collected in the back. So you set a bucket in the front and you get your small sample, and then the rest goes out the back. And you can split a bag 16-1. Okay. And then you can take that material and pass it through again. This is called a riffle at the bottom. And a riffle, okay, splits a sample into two bins. One half goes this direction, the other half goes that direction. And there are micro riffles that work on a surface of on a bench top, for example, that might split a 200-gram sample into a 100-gram sample. So this is, of course, a 1-to-1 split. Okay, but it's important not to take your sample and take your 50 pounds, split it down to a pound, and then scoop out 100 grams out of your 400 grams in the pound and say, oh, okay, I'm good, because you're still not good. You should split to the end. This coning process that we list here, the great photograph. This is a gravel pit. I used to take my students to the gravel pit in Alfred, New York, and I've got a great tour. It's a alluvial deposit from the glaciers, great material, and they do some crushing. A lot of it comes out of the ground the size they need. It's a massive operation. But the thing that's most interesting is that they crush this material to a specific size, and then it gets separated and it gets poured into a large cone, if you will. Okay. And this cone, there's a number of things here. One is you get a specific angle here for this, which is called an angle of repose. It's a natural angle for the material. So you can't stack it higher than that level, or else when it gets to that point, friction takes over or whatever, and the material will move. What's most importantly, and what I wanted to show you here, is that this process of making a cone segregates material by size. So you get coarse material down here on the bottom, okay? You get coarse material here at the bottom and fine material in the top. And there'll be very fine material up here to coarse material down here. So when you pour that material out, you segregate that material by particle size. And this is on a gross scale. This is gravel. So, these might be inch and a quarter in diameter down at the bottom, and they might be sand scale, so millimeter size in the middle, but it separates by size. So that's why when we go back to this coning and quartering thing, it works is because you're taking the quarters and then you combine them again and make another cone. So this material is allowed to segregate by size, but you can't scoop out of the middle or you get the fines only. If you scoop from the edge, you get the coarse only. So that's a problem. So this is the nature of the material. And of course, this only works if it's dry. Okay. So how do you measure density? We usually call it a pycnometer method. The common term, what you commonly see, is a helium pycnometer. Okay. And the helium pycnometer is a rather well-designed, interesting device. Uses a gas to measure the volume. You can use what's called a pycnometer bottle. So if you have a pycnometer bottle, which are small, they're typically 20 milliliters, for example. They may be larger. You can get, I think, 150 milliliters, something like that. But these are inexpensive. They're either stainless steel or glass, okay? And they're set up like this. They're a bottle, obviously. They often have a ground glass. If it's a glass bottle, has a ground glass top, and then the cap to this ground glass comes in and has a cone in it like this and a hole out the top. Okay, so you put your liquid in here. Okay, and when your liquid comes in to this, it you have the liquid in here with the bubble. The bubbles then are forced out and a little bit of liquid, so you get the perfect volume. And it's designed to be this volume is your 20 milliliters when the cap is on. So it is a finite, fixed, measured volume. And usually is associated with the temperature because of thermal expansion. Okay. If you want to measure the specific gravity, you can do that in a simple bottle. If you take a small neck bottle, typically, right, and you fill this with water. You weigh the bottle first, fill it with water, and then then the volume because the water is 1 gram per cubic centimeter. You can then pour your suspension in the bottle, screed off the top, measure the mass, and you have your specific gravity. So it's easy to calibrate. I had a student measuring packing densities years ago in a graduated cylinder, and he came back with data, and his data was interesting. Actually, theoretically impossible because he measured densities that were greater than what was possible, meaning that his density of alumina was like 4.2 or something like that rather than 4. And the reason is that graduated cylinders, okay, graduated cylinders come in 3 classes, okay, A, B, and C. C is called a student grade, okay, so that means it's approximately 100 milliliters. And then B is industrial grade, and A is research grade. If you're doing this type of thing for measuring density, get A. They cost more, but this is analytical grade. So they are, you'll see them right on there, written right on the cylinder. He used a C grade when he did it, a student grade. Okay, and that student grade turns out to not be 100 milliliters. It turned out to be what he thought was 100 milliliters was actually like 104 milliliters, something like this. Okay, so they call it student grade. And so if you go to the Fisher Scientific Catalog, you can find graduated cylinders. That's why we calibrate our graduated cylinders before we start. Put 100 grams of water in and look at where it hits the graduation on the side, and that's your volume. Okay. Pycnometer measures volume by a gas. Okay, so the way that it works, the clever instrument basically based on the ideal glass law, PV equals nRT. So what you do in this case is you have this volume. This is called a cell volume here. Okay. And you know the volume. And then you have a reference volume here. You know that volume. So what you do is you close this valve, you open up the whole system first, okay, and it equilibrates to 0. So you rate your gas pressure at 0. And then what you do is you close off this valve and you close off this valve and you pressurize this volume, okay, and you get a P1 value. And then you open this valve, okay, and when you open this valve, then that gas expands into this region and you get a P2 value and you can calculate the volume. So it's a very simple device. And then this at the bottom is actually the same device, but it inverts the system. So you have a known, same thing again, open the gas valves, etc. You know that you fill this with gas, and then you open this gas and it expands into this region. You have an expansion volume rather than a reference volume or a cell volume. And you say, well, why are there 2 different configurations? Is I think that one of these got around the patent of the other. So it's just a matter of whoever wrote the first patent missed the fact that you could do it a different way. The equations used to calculate the volume. So what it is that the volume of your powder, right? Volume of your powder is going to be what's occluded. So your volume of the cell initially is going to be greater than the volume of the cell final based on the amount of powder in that. And that's what you're getting. So basically, I think it's just a raw workaround. I say here that mineralogy may be possible. We did a bunch of work several years ago to get to mineralogy based on helium pycnometer and the measurement of density, density through helium pycnometer, elastic modulus or thermal expansion, there were a couple things that could be done and to get to mineralogy from density measurements. This follows what's called a rule of mixtures. So the rule of mixtures is I show it to you here. And why do you need this? This looks like a pain to work with. And so whenever you get these equations, people go, what's going on in the equation, right? So let's do this. Let's walk through this quickly. And so what I have is the rule of mixtures, ROM, okay? So if I take the fraction of A times the property of A plus the fraction of B times the property of B, I get the property of my sample. Okay, that sounds good. Now I have a problem. So the fraction of A could be in two different conditions, right? It could be on a volume basis or it could be on a mass basis. All right. So this would be in terms of, say, cubic centimeters. This would be, say, in terms of grams. So it turns out for rule of mixtures, for density, you would say the fraction of component A on a volume basis times the density of A. Notice I used the rho here for density, okay, as we did yesterday. Okay. Plus the fraction of component B on a volume basis times the density of B equals the density of my sample. Well, that's straightforward enough, right? So what happens? I have two powders. I mixed two powders. I mixed 60 grams of alumina, right, plus 40 grams of silica. Okay, so I can take my 60 and I substitute it in, and my 40, there's another equation. You need the fraction of A on a volume basis plus the fraction of B on a volume basis is equal to 1. Oh, that's good, because then I get, so for example, the fraction of A on a volume basis is equal to 1 minus the fraction of B on a volume basis. That all works. So then I come over here and I take my example here and I say, oh, all right, what I'm going to do is I'm going to say my fraction of A is 60. Okay. My fraction of B is 40, and you can say 0.4 if you want, and 0.6. Okay. But that's actually incorrect because this is mass. And so if I substitute these values into this equation, I get the wrong density of the sample. We say it's because this is on a volume basis, this is on a mass basis. I would have to convert this to a volume basis. So the equation then for density, okay, is fraction of A on a mass basis times 1 over the density of A plus the fraction of B on a mass basis times 1 over the density of B equals 1 over the density of my sample. Okay, this term is called a specific. I can spell that. So this is called specific volume. Which is 1 over density. So I'm telling you this because if you get a suspension, for example, and you take your graduated cylinder with a suspension, right, and you get the volume of your suspension, right, and you get the mass divided by volume, you get the density of the suspension, okay, that sounds fine. But then to determine the fraction of water and the fraction of powder, you need to do this either on a volume basis, which is fine, or you do it on a mass basis, but you have to do 1 over the density. So that is the rule of mixtures. And that is what's important about rule of mixtures, is that you have to make sure that you do the equation properly. So there's a lot of applications for this, but one more piece of information is surface area follows a rule of mixtures on a mass basis. So here we have, this would be specific surface area. This would be density. So they follow density on a volume basis, specific surface area on a mass basis, because specific surface area is meters squared per gram, whereas density is grams per cubic centimeter. Hopefully that's helpful. Okay. Specific surface area. BET, three guys, 1938. They are, oh, I didn't go away. All right. Brunauer, Emmett, and Teller. Same Teller from nuclear physics fame, 1938. They worked out this relationship. It was here, okay? And what it does, there's some misperception here, but they came up with a special case for absorption behavior. And they say that this corrects for multi-layer coverage. So what you're looking for is the weight of one monolayer, okay, which is this value, and that's 1 over W sub m times C. C is an interaction parameter, which is typically large, 50 to 300. And if that value is large, this can be approximated as 0, okay? And then this, C minus 1 over C, also goes to 1. So the slope of this line then becomes 1 over W sub m. And so that means that what you can do is measure a single point out here at 0.3, approximate that to go through 0, right? And you get your surface area. This is a small error then, minor error. And so what you can do is it corrects for multi-layer absorption in the system. This is the basis for all nitrogen absorption behavior, okay, is this simple relationship. Single point means that you're out here typically at 0.3. This is single point, okay? And if you're not, you do several different points along here, multi-point absorption. It gives you a specific surface area. That surface area is independent of the shape of the particle. In other words, it doesn't care if your particle is a sphere or irregularly shaped. It's giving you the actual surface area in the system, okay? Now, if that's the case, you end up with this, right? So if I have a sphere, that is the greatest surface to volume ratio. Excuse me, other way around. Minimum surface to volume ratio, okay? So if you have a sphere, the relationship is specific surface area, which is in meters squared per gram, is equal to 6 divided by density times diameter. Okay, so for a log normal distribution, this is your mean in the particle size distribution, and this is going to be in microns. Density is in grams per cubic centimeter, okay, and surface area is in meters squared per gram. If you do this, if you put in the density in grams per cubic centimeter and this particle size in microns, you get the surface area in meters squared per gram. And if you have doubts about that, go through and do the math, because it works out. It has to do with this is 10 to the minus 6 meters is a micron. This is 10 to the minus 2 meters, right? Which is cubed, which gives me 10 to the minus 6. Okay, and that works out to be 10 meters squared per gram. That's how it works out to be. Okay, so this is meters cubed. So when you do all of this, this assumes a sphere. What happens? If I put in a D50 and I calculate my surface area, my calculated surface area, so specific surface area calculated, is always going to be less than, sometimes quite a bit less than, my specific surface area measured. Why? Because nitrogen absorption, if I have a particle, okay, and I come in here and I absorb nitrogen on the surface of that particle, well, it's going to absorb into all the little nooks and crannies of that particle. And also, it's going to give me the best case could be if it was a sphere. Okay, well, it's not a sphere. So anything I do to deviate from a sphere increases my surface area. Here's a simple example, and you can do the math to figure it out. I have a sphere. Oh, now I have a half sphere. Well, I took my surface area of a sphere, which is pi r squared, and now I added to that, I half that because I have a half a sphere, and I added this area. Well, it turns out that I didn't quite double my surface area by splitting my sphere in half, but I increased my surface area. So what will happen is that in specific surface area measurements, the measurement that you get from the instrument will predict a much smaller particle size than you measure through particle size techniques. That means your D50, based on specific surface area, will be much, much less than your D50 measured. Okay. So what does this mean? That means that you cannot predict the surface area from a particle size measurement, nor can you predict the particle size from a surface area measurement. And instruments do this automatically. They will take your particle size data and they'll calculate the surface area. That piece of information is useless. Why? Because they have made an assumption, and that assumption is that your particles are spherical. And your particles are not spherical, with very few exceptions. And even if they're spherical, let's say you have a golf ball, the surface of a golf ball has all the dimples in it. That increases its surface area. Okay, so just keep in mind, they are independent measurements, surface area, particle size distribution, and density, but they can be used to understand more about your powders. So let's talk about particle size distributions. Ceramic powders are typically produced by comminution. That means grinding, okay? So your powders are produced by particle size distributions. We'll say crushing and grinding. Okay. That process typically generates what's called a log normal distribution. Okay. So you get a particle like this. Oh, it breaks off like that. That would be ideal, perhaps. But maybe it's shaped like this and it breaks a little part off, right? And so what you get is that attrition, that grinding of these powders gives me a distribution that is broad, very broad. We're going to talk about particle size distributions here in a minute. Okay. All of my particle size measurement techniques assume a spherical particle. That means if I looked at, let's say I have this particle, then I would come up with some shape or I would not shape, I would come up with a sort of a sphere that represents that particle. And you say, well, you could argue that it follows this smaller size, or it could end up following this larger size. Okay, I agree. There are some flaws in the system. However, this information is really useful. Even though it assumes that the particles are spherical, we still get very useful information out of it. So sieves, okay, testing sieves, right, they work above 38 microns. Why? What happens with 38 microns? Well, there's a number of practical considerations, right? But one is that particles that are greater, this should be microns. Particles that are greater than 38 microns flow freely. Go into your kitchen, get the sugar out or get the salt out, okay, and pour it out, and it pours nicely. Go get the flour, try to pour it out. It doesn't flow nicely. Or to give you a better example, go get confectioner's sugar, powder sugar, and look how it flows compared to granulated sugar and how it flows. Okay, that's the difference. The granulated sugar particles are larger and they flow freely, just like sand flows versus clay. Okay, and the powder sugar does not flow freely. The reason is that when the particles get below this cutoff of 38 microns, you end up with agglomeration because of what are called van der Waals attractive forces. This cutoff is called the colloidal limit. And colloidal forces dominate over the forces of gravity. So when the particles get too small, they start to become immune to gravity and they clump instead of flow well. There's another practical condition for 38 microns. We can go just a little bit lower, but the practical consideration is wire size. Okay, so what happens in these systems is we have a sieve. Now, I have a really great image here. This is fused silica that was screened. The top here is 200 mesh. Okay, so 200 mesh is 75 microns, and then the bottom is 325 mesh. Now, the way that we try to do electron micrographs is to be consistent in our magnifications. So if you see here, this is 1 millimeter here, and it's 1 millimeter here. So these two images are at the same, these are at the same magnification. Then over here, this is 500 microns, okay, and this is 500 microns. So these two are at the same magnification. Drawn in here in the square is a 75 micron hole. Okay, this would be the size of a sieve opening size for 200 mesh. Okay, now what will happen is all of these particles on the top were caught. Okay, they were caught. Oops. Maybe I can spell later today. Okay, they were caught on a 200 mesh. Okay, and that means that they all should be larger than 75 microns. These powders here, these are 325 mesh. They passed 200 mesh. So all of these particles should be smaller than 75 microns, but they should be larger than 45 microns. So here's my 45 micron hole, if you will. Okay, so here's my 45 micron hole, and here's my 45 micron hole. And all of these particles then are sitting on top of a sieve that's composed of 45 micron holes. And so what you see in this image, or what you should see in this image, is all these particles in both images, from here to here and here to here, look similar in size. They're not exactly the same, but they are similar in size. Okay, so they are captured on the screen. So how do testing sieves work, or testing screens as they're called? We have a number of, there's these two manufacturers, okay? They're called USA Standard Sieve Testing Sieve, okay? And there's a number here, ASTM E11. You can go look this up, okay? Because this gives all the specifications for testing sieves. And you'll see it says right on here, E11 specification right here. Testing sieve, E11 specification. Now, this is a 3/8 inch, okay? And then it has a Tyler equivalent. So W.S. Tyler, I think, invented sieves. I may have that wrong. But they came out with standard sieve sizes that were then eventually adopted as a U.S. standard. There are standard sieve sizes for many different organizations in the world. ISO has one. There's a European standard. There's a U.S. standard. Other standards in other places. Now, this number, for example, 200 here, is approximately the number of holes per inch. So if you see a lower number, smaller number, that means there's fewer holes per inch. So the opening size is larger. Okay. And if you get a higher number, they're greater. The greatest sieve number is 400 mesh. It's called a 400 mesh. So that's the mesh size. This is called a mesh size. It's an approximation. What does that mean? Well, this number is useful for identifying the sieve, but is useless for identifying the particle. Okay, so number of holes per inch is about 200, and so you can do this sieve number calculation, and there's some information here that's provided for you. Okay, but what you want is this: the opening size is the important part. Okay, how big is that opening? And it's listed on every sieve. Okay, 400 microns, 75 microns for a 200 mesh. Here's 1.4 millimeters. Okay, so that's your opening size. That's what's important. Sieves are remarkable devices, and they are because they were set up extremely well. This is your mesh size here. Okay, and this is your opening. Now, what you'll notice here is that if I go 4, so if I go from number 18, and then I skip 1, 2, 3, when I get to number 4, I am now 2x. So that means that 18 is twice the opening size of 35. Okay, so what I've done is if I kept going, I could come down here and say, here is 18, 35, and then I go down 4, 1, 2, 3, 4. Number 60, 1, 2, 3, 4. Number 120, 1, 2, 3, 4. Number 230. Okay. I could stack these sieves up. Okay. And I could measure powders that range from 1 millimeter or larger. Okay. Because they'd be captured on an 18 mesh down to 63 microns in a single sieve stack that only has 5 sieves in it. What we typically do is this: every other sieve, that's a square root of 2 basis. Okay, so I might say, often we start at the bottom and say, well, I'll do 325, 230, and then 170, 120, 80, and then 60. Okay, 1, 2, 3, 4, 5, 6. Okay, that sounds good. I could probably do 7 maximum in the thing, plus a pan. So there's a closed thing that goes on the bottom, closed pan that goes on the bottom, a closed sieve that captures everything and passes through 45 microns. Why 7 or 8? I think 7 is the limit for my testing device. And I have a picture of it here. Let's see how many are in there. 1, 2, 3, 4, 5, 6, 7. Okay, so 6 plus a pan. Okay, so I can do 6 plus a pan in a typical sieve stack. Now I'm going to tell you why we need to do a row tap in a minute. So you have 6 sieves plus a pan. So I can go from 250 microns to 45 microns. This is a log basis. Log particle size basis. Because I am geometrically changing the size in between my sieves. If I go every sieve, it's the square root of 2 over 2. So if I take 90 divided by 75, I get the ratio of square root of 2 over 2. 355 divided by 250 gives me the square root of 2, which is 1.414, approximately. Okay. So I can set my sieve up with the square root of 2 basis. That means that the sieve above is the square root of 2, 1.4 times larger than the one below, and the one below that is 1.4 times smaller. So I'm geometrically changing the separation between my sieve sizes. That will give me a log normal distribution. Okay, why? Why is that important? Because everything is produced by grinding. And grinding produces, by and large, a log normal distribution. Okay, so I've got some great pictures of sieves just so you can see. Square holes for round particles. They're assumed to be round. In the background in this screen, you can see the larger sieve below it. Okay, so there's a line here like this, right? And then you can see the large sieve below that. And then to give you some scale, there's a penny. Okay, I don't remember the size of the sieve. It's not particularly important. You can see that the wires are crimped around each other. This is your wire mesh. This is your sieve opening size. Okay. And it's a square, so it works out very nicely. Now, the other thing you might notice is that if you were to use this sieve for a long period of time, these might wear, and the wires might wear. Brass sieves last not as long as stainless steel sieves. We did some sieving a while back and started to pick up copper in our material after sieving, and it was because we were braiding the brass sieve. That means you have to check your sieves periodically for wear, or else your particle size distributions will appear to grow. Okay, but this just gives you an idea of the scale. Okay, the penny is obvious, and then I like this one. I think this is a 230 mesh. It's not very clear, but that's the benefit of a cell phone. So what happens is as you go from here, okay, you can see the wire size to here, the wire gets smaller, gets very small here. Okay, and this is why. If I have a big wire like here, then the particle has this whole area. I can pick up a big particle and clog it in here, but a small particle will clog this screen also. And I want my particle size and my wire size to be roughly similar. So there's a chart. This comes out of ASTM, and there's some really good references for this. And if you want them, I'll provide them. Wire diameter here, okay, as a function of sieve opening size, and this is your curve. So these are designed, they're done very, very well, and they try to minimize clogging. If I go up to this picture here, you can see in this picture that there are some particles clogged in the screen. Okay. Now, also with really fine mesh sizes, you have to be careful of how you clean the sieve, or else you damage the wires. So ESTM standards are listed here for sieve amounts and sieve standards. And there's a limit. So how much you can put on a sieve. And typically, I'm not a fan of wet sieving, and I wouldn't recommend doing it. And if you want to do wet sieving, we can talk about it. There's only specific applications that really work. The best way to do wet sieving is to remove the fine material to allow the coarser material to be separated by sieve. So we might wet sieve through a 400 mesh and then dry what's left and do the regular sieve. So refractory mixes that have extremely broad particle size distributions that scan a few orders of magnitude might have a clay binder system in there that's less than 10% of the batch, often down in the few percent range. So you would water sieve the clay out, and then you can characterize the rest. Why do we have a limit on how much material goes through the system? So there's a contribution of density, okay, and there's this is an average weight. This value here is obviously not the density of alumina, but this is approximately 50% of the density of alumina. You say, why? Because powders pack to 50% in a dry state, usually if the powders are above the colloidal limit. So what they're trying to do is figure out what volume of powder can I put on the sieve? And if I put too much powder on the sieve, it doesn't work. You say, how does it work? Well, you may laugh at the Rotap as a device, and the Rotap is a device that rotates the sample, okay, and also bangs it up and down. So it rotates and bangs at the same time, and it's if you put too much material in the sieve, it doesn't work. So how does this process work? The way that it works is that sieve analysis is a statistical process. What does that mean? That means that I have to find a hole. So if I put all my powder in there, then the powder has to find a hole. So if it can't find a hole, then it doesn't fall through, and it should fall through. So I end up with a poor sieve analysis. That means I have a specific amount of time necessary to find a hole. And that time is approximately, believe it or not, 20 minutes. Okay. And the time to sieve is roughly 20 minutes or a half an hour. But if you do 5 minutes, you don't get a representative because of the statistical process. So what happens is that when this thing bangs, okay, all the particles on the sieve lift up, get suspended, and then it rotates, and the sieve moves, and the particles sit down in a new location. And then it gets banged again, and then they lift, and they set down. They lift, and they set down. And so what's happening is they are moving in that system. And that is a remarkably efficient way to do this. The tap suspends the particles, and the rotation, moves the sieve so that the particles have a greater probability of finding a hole to fall through. Okay. Ideally, they move to a new area that's not clogged. If they're overloaded, the material in the sieve can't lift, and the particles then are impeding other particles from finding holes or fall through the sieve, so you get a non-representative measurement. If this is done properly, it's a remarkably useful and reproducible technique, but it is limited to particles which are typically greater than, say, 30 microns. Okay, you've got some room here, but 30 micron particle would fall through a 38 micron hole. 38 is my smallest sieve size, and that was up here. Okay, when we look at this, 400 mesh is 38 microns. 45 is typical for us. Okay, so I can have particles smaller than that, and they will fall through all the sieves, and they will end up in the pan, and I'll be able to measure them. Okay, so if I take a fine powder, though, which is less than my 38 microns, so this is a powder called, it's a calcined alumina called A10. And I can sieve it, but what do I get? I get a weird result. If I take really fine powders and I put them on a sieve, they bounce around in the sieve and they undergo this thing called a triboelectric effect, and they pick up a charge and by friction. So you know how you take the glass rod and rub it with rub it with wool, you get a charge on the rod. This is like what we see in grade school, earth science classes or whatever. Well, the particles do that actually. They actually generate a charge, and that charge makes them stick together. So they'll agglomerate on the sieve and not go through. So I can take a powder which is much smaller than 45 microns, and it will be caught on a 100 mesh sieve or something like that. Meaning that I have 150 microns of half micron powders that will not sieve. So if I pack that dry, I get a packing efficiency, okay, which is large. So that means that packing efficiency is small. So here's my volume dry. If I put it in water, this volume shrinks to this point. This is approximately 50%. And if I add a dispersant into the system, this then further decreases, okay, to give me an improvement in packing efficiency. So the way that I treat my powders affect their packing efficiency. Adding water reduces the van der Waals attraction and the particles pack better. If I add water to coarse particles, nothing happens because the particles are too large and the van der Waals attraction forces are unimportant. If I let these powders settle, so what's interesting is I can put these powders in this condition here, in my flocculated case, and I come back a day later and they're all settled like this. Here, in this case, you see these powders here, okay, are still suspended. Okay, these are very fine powders. They're probably less than 1 micron. And it might take them, a week to settle or several days, we'll say. Okay, so this will take a long time to settle, and you can see approximately where they're at. And then this volume may change slightly, but you can see there's not many powders here, many particles here. So this is probably going to stay the same, but you will see that this cloudiness will go away with time. If I take just a typical suspension and I put it in water and look at the settling time, the powder is not particularly important, but this is a clay, so it's a half micron, typically about 0.5 microns. I have, this is Stokes sedimentation equation, and here I have a velocity term, and that is x distance divided by time. Okay, so I don't tell you the distance here, but this was in a graduated cylinder, and it takes roughly, this is 24 hours, here is 20, 30, 40, here is 48 hours, 2 days. It takes approximately 2 days for it to settle out to become a constant mass. Okay, but that's because I have a small particle. So this is sedimentation. We're going to get into that for particle size here in a moment. I'm going to tell you something else about particle size distribution. What does it mean to be log normal? So this is the data that I get out of, say, a Cetograph, okay? Now, if you look at the original Cetographs, and if you look at the sieves, right, and I go back up here to the sieve stack, which you cannot see very well. Maybe I can show you. Stand by. Probably not, but I might be able to. Okay. The way that this works, okay, is that this is the largest, and this is the pan here, and this is the smallest size, right? So when I take the sieve stack apart, I measure the largest first, I measure what's on this sieve first. This is number 1, then number 2, number 3, number 4, number 5, of course, and number 6. And I plot that on a plot. I have particle size. This is log particle size. So I have 1,000 here, 100. Okay, well, I should do that a little bit differently, but not by much. Here's 100. This is 300. And so what I do is I do my mass on this axis, and I measure the largest first. So my particle size distributions are inverted in terms of the scale. Large on the left-hand side, small on the right-hand side. So this is going from large to small, because that's how the sieves were set up. When the Cetograph first came out, it did the same thing, okay? And it measured from large to small. But we don't like that. And now we computer graph everything. So now we go from small to large. So this is inverted from what you would have seen from Cetograph data before. And you say, why do they do that? Cetograph evolved from a technique called Andresen pipette, which is a sedimentation technique, and it measures the largest particles first. So then when you see the graphs, they're always inverted, because that's how people were used to it. And when they developed the Cetograph, they couldn't change everything. People had to see what they were used to seeing in order to have confidence in the instrument. So I get a particle size distribution here, and I apologize, these aren't lined up. If I deconvolute this, I get a distribution based on this, right, which is here. This curve should be here, like this. Okay, so this is a Gaussian distribution, or a bell-shaped curve, on a log scale. And if this is symmetrical on a log scale, essentially it is a log normal distribution. So you get a curve like this. This is our cumulative mass finer than. So you see cumulative mass finer than comes also from the sieves. So you're going to measure what's on the sieve. How much is on the sieve? Oh, okay, I've got 80% on the sieve. That means that 20% of my material is going to be finer than that. Okay, so that's my cumulative mass finer than. We started working with this several years ago. If I get what's called a probability axis, this is a probability axis, and I do, it is a Gaussian curve like this in terms of the scale. If I take this data and I plot it here, I get a straight line. So our thoughts were that we could characterize this distribution by a mean. This is my D50, and a slope. This is the width of my distribution. Okay, we're still working on that, but this is what it means to be log normal. Powders that are produced by milling or comminution tend to be log normal. Powders produced by agglomeration or precipitation events tend to be normal. What does that mean? Well, if you were to go back to the slide, if we go back to this slide for a second, okay, you might argue in this slide that all of these particles are the same size. That would be normal. You would argue that's a normal distribution. The fact is that when I look at actual powders, they're not all the same size. And I have boulders and I have fine particles in the same field of view. That would be log normal. So my powders produced by milling tend to be log normal. In the industry, you scalp the distribution. So you'll come into this distribution, you'll say, okay, I'm going to get rid of this, and I'm going to get rid of this, and I'm only going to work with what's in the middle, okay? Then I've scalped my distribution, and now my distribution is log normal, but very narrowly distributed. So you buy powders based on that. So we've done a lot of work with this, and one thing is if I take, say, silicon carbide powder, fine grain silicon carbide powder, if it's flocculated, it tends to give me this curve. This is my Gaussian axis again. Okay, so this is the probability axis. And if I'm dispersed, I get a nice straight line. little bit of a curve at the bottom, but I get a straight line as I eliminate the agglomerates. So agglomerates cause my particle size distribution to broaden, and it also changes the nature of the distribution. So I can use that actually as a tool. I think it's beyond the scope of this class, but I'm going to teach a class in a few weeks called Introduction to Ceramic Processing. And I will go into this in a lot more detail because I think it's very valuable industrially. So how do we measure fine powders? Now we're measuring powders that are less than 38 microns, or 38 microns, for example. How do I measure powders that are less than 38 microns? There's a number of techniques. In my opinion, X-ray Cetograph is by far the best technique, okay, bar none. It takes Stokes sedimentation law. Diameter is 18 viscosity. This is viscosity here. Oh, they didn't show up. Wait, I can fix that. There we go. Okay, suspension medium viscosity, particle velocity is here. Okay, and then this is the density difference between my particle here and the fluid, and this is gravity. Okay, so what's great about this is I can take my powder in a helium pycnometer and I can measure this density. And the density of my fluid, if it's water, I can look it up based on temperature, get that value, or I can measure it through also a graduated cylinder or pycnometer method. Okay, and then I can calculate what the diameter is based on the sedimentation time. This instrument, the X-ray Cetograph, does that for me. So what it does is it sends X-rays through this cell, okay, but it sends them through the cell. Actually, the X-rays are stationary. The cell moves down. So it starts off measuring at the bottom, largest particles first, and then it measures to the top, okay, bypassing X-rays through the cell. And if all the particles settle at the top, which is at this end down here, this is the top, this is the bottom, okay. There are no particles at the top, it goes to zero, and I get my curve. Why do I like this? I like this because I can measure the density. I can make corrections to the data, and I can measure the viscosity of the fluid, etc., as necessary. And I can then deconvolute this data to learn about my particle size distributions. Okay, what's the downside? The downside, the negative, is time. It takes time to settle. Now, the X-ray Cetograph cuts off at 100 nanometers, 0.1 microns, because of a misunderstood argument that they're arguing for Brownian motion. If you wish to talk about that, we can do that later. Okay, so that brings us to light scattering. If you have ever seen me in a conference where we talk about particle size, you will already know my bias that is strongly against light scattering and laser scattering, okay? And it's not without basis, believe it or not. All right, so here's the deal. The literature indicates that they can reliably measure particles down to 20 nanometers. And 20 nanometers, that's reasonable, okay? Some may measure it for lower than that. Very fast. It measures in minutes because it's not dependent upon sedimentation. It's looking at the scattering of light through the system when it hits a particle. So you have a particle in suspension, light comes in and then it scatters. Okay, and they look at this as a diffraction pattern basically, and they determine from this distance here what this particle size is. Very broad spectrum, very broad view. Very small specimen necessary. That's great. Okay, maybe reasonable for QC applications only. Why? Because you're probably only interested in a D50. And this technique will probably give you a reliable D50. Okay. The issue is, though, here, when I do that, I'm fine, but this measurement technique requires that I know the refractive index of my powder, which is a difficult value to get. And in fact, there are two components, a real part and an imaginary part. Imaginary. Okay, and the imaginary part actually is important for particles which are opaque. Okay, imaginary. So you have two components to every refractive index value, okay, real and imaginary. That's a very difficult number to get. And it's important because of how it treats that data, and it needs it for looking at the scattering behavior. Instrument makers, everyone is different. There's about, I think, 6 people right now making a laser device. They all have a proprietary algorithm by which they use to characterize that data, and they don't share that. So you get the data back. You cannot do anything to alter the data or evaluate the distributions differently. I'm not talking about manufacturing data. I'm talking about how do they get the measurements. They won't tell you. They just give you the distribution. And the fact is the distributions are, for lack of a better term, funky. Okay. Because of this technique that we've been working on to look at our particle size distributions differently, we then applied that to laser scattering. Okay. And so this is laser here. Okay. This is X-ray sedimentation. So this is my cumulative mass finer than plots. Here's my A10, which is alumina. Okay. And here is silica. And this is the distribution that I get from the Centigraph. Well, that makes some sense. You say, why is this cut off at 100? Is that in the Centigraph, we sometimes get noise. It comes up to the top and then it does something like this. And the problem is that people interpret this as being important, and these are just imperfections that we run across, and we can discuss that if you wish. That's this tail up here. Look at my dynamic light scattering data. It tells me my A10 has this long tail, okay? And I don't understand what's going on here. What creates a step in this? It says that I have no particles in this size range. I have no particles in this size range, okay? And I don't understand what's going on. But notice that this is telling me that I have no particles roughly less than 30 microns in my silica. This is telling me that I have 80% of my particles are less than 30 microns. Something's not right. And I know what you're going to ask me. It's like, how do you know which one's correct? Well, when we plot the data on using, this is a Weibull distribution, which is another statistical analysis technique. I get essentially straight line data from my alumina, and I get straight line data for my silica. This is showing me a bimodal distribution in alumina and a trimodal distribution in my silica from laser scattering. The same technique done now through a Gaussian distribution. This is my probability axis. I get reasonable log normal distribution for a portion of the curve. Same thing here, by the way. A narrow distribution for my silica, 2 distributions potentially. But I get this funkiness again in my silica. So where you might be able to use this is to come back and do the D50s, okay? So if I do the D50 here, right, I get a value for this and a value for this. I do my D50 here. I don't get the same value for both, okay? Probably be better to change the color to see that here, okay? So I don't get the same value for both. But if I was looking at my A10 suspension every week to see if my raw materials were coming in to the system and what I'm getting from my raw material supplier is reliable, this may be sufficient for me to identify a large excursion. But you see the alumina here comes down, it's pretty close. We're somewhere around 8 to 9 microns. Here we're somewhere around 7 to 8 microns. So my alumina is pretty good. My silica, though, is way off. Okay. So I'm not a fan of laser, and it's not likely I'm going to change my mind anytime soon. So I think at this point, if you're good, we're going to go into ceramic forming processes next. And what I think would be good is if we take a short break here, if that works for everybody. And we'll welcome back. Any feedback from me? For me, not from me. Pace is good. Information useful. Blah, 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 blah. Anything? Okay. We're going to keep going if that's good. So that brings us to ceramic forming processes. And this is by nature going to be a pretty high elevation view because of the restrictions of time and the fact that there's just so much information that's possible. Um, I also, I mentioned the ceramic processing course, and we do a lot of stuff with rheology, suspension flow, suspension control, and things like that in that course. But I just think that the scope of this course as an introduction is that's too specific to be really useful. I think the particle size distribution, particularly for people who are technically involved in ceramics, is really useful in being able to characterize powders and understand why we do that. But I think that going into too many details here would be less beneficial. So we have essentially in ceramic forming processes, we have those that involve a lot of water and those that involve almost no water at all. So this is the no water side down here to speak of, at least in the pressing operation itself. And then these are all what are called saturated systems, if you will. Okay. Saturated, it means they have more water than is necessary to fill the pore structure. So these two are also called plastic forming techniques, meaning that you plastically deform the body, whereas this is the slip casting is a suspension technique. So slip casting is not the oldest technique. I think you would argue that a pinch pot, which is a plastic forming technique that's actually somewhat similar to extrusion, might be the oldest forming technique. And then you get into wheel work or throwing, which has obviously been around a long time. But slip casting then comes in probably around that time. So you have a suspension of particles called a slip. That term comes from the fact that clay particles in suspension tend to be slippery. Okay. And so they were called a slip. They usually use a gypsum mold, and a gypsum mold is sometimes referred to as plaster. Okay. Plaster of Paris reacts with water to form gypsum. And so we have a gypsum mold, and you're able to do complex shapes with a lot of detail potentially, but it is very labor intensive. Okay, because you need a skilled laborer to manage the process. They have to be skilled in how they handle the piece when it comes out of the mold. The piece when it comes out of the mold is often easy to plastically deform. It deforms easily. It's has a lot of water in it. It's not particularly strong, but it is pliable. And that pliable aspect of it is actually a problem for you because if you deform it, it will retain that shape or may have a memory of that shape. You get the highest shrinkage, usually isotropic or relatively isotropic. And isotropic means it's the same in all orientations. So that means if I were to take, say, let's say for sake of argument, I have something like a cube, like this, or a rectangular cross-section piece. Okay. The shrinkage in all directions is going to be roughly the same. Okay, that's isotropic. If it's anisotropic, it might be much more in one direction than in another. And so usually slip casting gives me isotropic shrinkage. Ram pressing is a different process. Plastic body, meaning that you have a little more water than is necessary to fill the pore structure. You're not able to do as much detail, and usually for larger objects that are difficult to reproduce or difficult to make. Low shrinkage, high uniformity. We could add into here a process called jiggering, okay? But jiggering is typically restricted to traditional ceramic processing, whereas I've seen ram pressing in some advanced ceramic applications. And then we get to extrusion. Plastic body, again, uniform cross-section, high density. Low shrinkage in general, lower than slip casting, similar to ram pressing, but isotropic shrinkage. Dry pressing, we're going to spend a little more time on granulated feed from a spray dryer, okay? That allows us to work with finer particle size, less complex shapes. This dye fill is critical, and we're going to talk about that. There's no drying shrinkage, which is nice, and it is typically isotropic. Here's a cartoon approach to slip casting. You have, it says a plaster mold. This is gypsum. So here's the difference. Calcium sulfate with 1/2 water. This is plaster of Paris. Okay. We add to that 3/2 water, which is what we need to complete this reaction. Gives us ideally reversible, but not in reality, CaSO4, calcium sulfate 2 waters. This is gypsum. Okay. This is our mold material. If we increase the water content, I increase the porosity in the mold. Okay. And with an increase in porosity, I see a decrease in mold strength. So a decrease, we'll call it abrasion, decrease in abrasion, meaning that the mold can be abraded as I increase my porosity. More porosity means there's more water. Okay, so there's a trade-off here. Okay. If you make gypsum molds, you dry them without heat because this reaction, calcium sulfate, okay, goes to what's called anhydrite, CaSO4 plus 2H2O that comes off as gas, okay, at about 96 degrees C. And this is now your molds crack. They don't work as molds anymore, and you destroy your molds. So it's a typical undergraduate thing. They get a new mold in and they put it in the dryer, and then the mold is destroyed. So this is a process called drain casting here. Okay. Okay. And drain casting, you pour your slip into the plaster mold, the gypsum mold, excuse me. And then what happens is that water is pulled in by capillary action. Okay. Absorption. This is capillary action. Pulls water into the gypsum capillary. Okay. Water wets the pore walls of the gypsum, pours water in, and deposits behind it the particles. Okay. The thickness of that cast layer scales with the thickness of the cast layer with time to the 1/2. So that means that if you double your time, so if this is, for example, 1, 4, 9, 16, okay, you'll get a linear behavior. If you do this on a time basis, though, thickness, we'll make it TH like that, curve looks like this. So when you look at that, you go, oh, it's done casting out here. It's not done casting. It's just that this is now needs to be on a log or a geometric scale. Okay. And so this is how your thickness builds up. So the misnomer is the problem is that people like to do this to look at casting behavior. They take the slope of this initial time, which is not a slope, but it's a curve. And they go, I'm going to look at my cast thickness at a given time. But really it should be on this other basis. So what will happen is that once you start casting, the casting rate essentially slows down because of hydraulic resistance in the cast layer, slows down the rate at which water can move through the cast layer. So your wall thickness builds up non-linearly. When you get to the desired wall thickness, you remove the excess slurry by pouring out. That's the drain part. Okay. Then you allow the system to dry partially, and in drying, it shrinks. Okay. So it shrinks to go to this stage. And when it shrinks, you can remove the piece from the mold. Okay. So that's essentially slip casting. In sanitary ware, they don't drain the system. They cast two walls. So you have your mold and your mold. Okay. And you bring in your slurry, basically. Your slurry comes in and it casts into both sides at the same time. And when you get done, you have a parting line down the middle that's usually not too bad, and you can see it in cast layers. Okay, so this is sanitary ware. Okay, and it's called solid casting. Need a bigger piece of paper. But that's high elevation view of slip casting. Oh, one other thing. Why plaster of Paris? Why use plaster of Paris? It is a inexpensive material, readily available, widely distributed. From a geographic standpoint, there's a band of plaster that runs from Oklahoma up to Nova Scotia. Just depends on how deep you want to dig for it. And so it's not plaster in the ground, it's gypsum. They mine it, they gently heat it to drive off portion of the water, 3/2 water, and they get plaster of Paris. Big application, wallboard, right? I mean, this is essentially sheetrock or wallboard. So we are in the ceramic industry in what's called the industrial plaster regime. We are a minority player in this industry. Wallboard is the lion's share of the industry. I don't know what the amount would be. Ram pressing. Again, this is a gypsum mold, but it's special. This gypsum mold has reinforcement in it, okay, which I'm just going to draw here as a crosshatch, reinforced, and then it has a series of tubes that go through the system that come out to be to a fitting, and then this goes to a hose, okay, to a compressor, okay. And what they do is they, when they press the mold, they will pressurize this in the mold through this pressure. Okay, they force air in, and that causes the piece to release, and then that action of pushing air into the system causes the piece to release. It stays on the top, and then they have the same thing on the top. They have the tubing in here, basically. And so that tubing in here at the top, then what they do is they pressurize that. Okay. So then they put a board under here and they catch the piece when it falls off. Not a big piece like this, but that's essentially how they do it. Like if they're making dinnerware, large casseroles or whatever, they keep it on the top mold and then they release it to the bottom. This picture is okay, but in fact, you'd rather see this picture look more like this with the draft angle here rather than being straight wall, because straight wall doesn't work. Okay, so this way the piece then, when it comes off of here nicely, okay, to give you your wall thickness. Now there's an interesting and fascinating thing about ram pressing. If you take a piece of clay, okay, now this is usually extruded clay, and that's this piece here, by the way, okay. And you put that, if you draw an X on here like that, and you put it in the ram press, when it comes out, you get your sheet, your casserole or whatever, with your walls on the side, okay. I'll do it like this. The X does not expand. It's the same size as what you drew on the piece. This X becomes that X. So what it means is that in the ram press, when you're coming down on the ram press, okay, what you have is this, your platen, okay, and your clay. When the clay forms, when the system deforms the clay, it locks in the system and it moves out this way. But this area in contact stays in contact. So the clay is getting squished out the edge. Now, what does that mean? Well, that means that if you put a piece of clay in that's exactly the right size for your piece, the velocity that it has to move becomes too great and you start to tear the clay. So the rule of thumb is that this piece here is 1.5 times greater by mass than this piece here. So that means that you have, let's just say for sake of argument, you have a 1 kilogram piece that you're making, you're going to put 1.5 kilograms of clay in. And that is, you'll never find that published someplace. That's a rule of thumb in the industry. The same with jiggering. You end up with the excess material gets pushed out through here in the ram press, And usually there's some detail in this mold that allows this to pinch off that clay. This piece then goes out, goes right back in, it gets reused again. But you have to have that excess material to make this process work. And the same with jiggering. Years ago, before we understood the process very well, I was called by a company making flower pots, and their yields were terrible. And the reason their yields were terrible was that flower pot is a deep dish, if you will, like this, so you're of course familiar with flower pots, right? He was putting the amount of clay in to make the flower pot, and he should have been putting in 1.5 times the amount of clay. But he was trying to make exactly the right amount of clay to make the flower pot. And the consequence was his yields were very poor. Unfortunately, I think he went out of business, but I haven't heard from him in years. Extrusion, there's so much information about extrusion, but essentially uniform cross section. Most extruders, industrial extruders, you have a barrel, and then down the center of the barrel, you have a shaft, and you have an auger in that barrel, okay? And the auger then pushes the clay. Basically, as the auger turns, I don't know which direction it turns, but it pushes the clay out into a die. And so there's a lot of technology associated with this. One thing that they do is they'll have an auger of a certain size, say 8 inches in diameter, and then they'll go into, it should be inches, not feet. Then they go into an expansion chamber, okay? And then they go into a smaller chamber, basically, or they're able to increase the size of their I think they go into a die then that might be, say, 12 inches in diameter, right? So you go from 8 inches here, they go to 12 inches here by this expansion chamber, and then they extrude. Biggest extruders are typically, this is for terracotta here. Electrical insulators. There was, I'm not sure it's still there, in Baltimore, Maryland, there was a Lock Insulator Company. They had an extruder which was vertical, and it would extrude a piece of clay, um, uh, 8 feet long and 4 feet in diameter. Oops, I said inches, not inches, feet. Okay, so we'll say 48 inches in diameter. And they would, this was 3 stories tall. They had to put a ton of clay in to turn the thing on, and then they would extrude down and make these huge cylinders. How does it work? It works, we've done a lot of research on this, and ceramics in general, traditional ceramic bodies are intrinsically plastic. They work great in extrusion. But the general rule of thumb for extrusion, we determine something called available volume. It means you need a little bit of excess volume over what is necessary to fill the pores. Over to fill the pores. We take our general rule of thumb of 50% pore volume, all right, for a packed body, which is not a bad assumption. We find that we need approximately 6% excess liquid, in this case water, to create extrusion. Okay, so this is predictable, if you will, based on powder packing, and you can get to that point. But what we find in the system, and this is important here, what we find in the system is that we work on a mass basis. The ceramic industry, by and large, works on a mass basis, right? So mass basis. That's fine, except, and that actually makes it a lot easier, by the way, for batching, of course, because we don't have a way to measure powders on a volume basis, right? But what we do have, what we need is a volume basis. And here's a problem. If I'm alumina, I'm at 4 grams per cubic centimeter, and water is 1. So 1% by weight is 4% by volume. Okay. So I have to correct for that. That's why this becomes important, because if I was close and I add a percent water, I just leaped over I couldn't even leap over my window. This is 6 to 8% excess water is what it's supposed to be. But the idea is that we need to be thinking about this on a volume basis. So if your system is too stiff, you may have to add 0.25% water rather than 1% water. And the example I use is making pancakes. You add a small amount of water to the batter, and you think that's not enough, and then you add a little more, and you add a little more, and soon you add too much. What do you get? You get crepes. All right, let's talk about dry pressing. This is the most common forming technique for ceramics. High production rates, easy to automate, high yields, typically limited to simple shapes, tile, bushings, thread guides, etc. Low moisture content, no shrinkage. Okay, easy to maintain powder flow, and overall it's well understood. But here's the bottom line for dry pressing. Most important thing, die fill is critical. We believe that the particles rearrange in pressing. So if I have a press die like this, and I have my die, and I have my powder in here, and it does something like this, okay? My assumption is that when I press this, and I did this intentionally to have this sort of gradient here of powder in the system, okay? And when I bring in my top die and I push on it, I have an assumption that that powder is going to nicely rearrange for me to fill that space to give me uniformity. And that is not what happens. There's almost no lateral movement in the system. Okay. Now, that's exciting from one respect. They make tile now, ceramic tile, 3 meters by 2 meters wide. So that means you get a tile, looks like this, right? But this is 3 meters and this is 2 meters. The die, though, looks like this. Flat plate, okay, bottom die. Your top die is a flat plate, and there's no edge. The powder comes in and it makes this edge itself, okay, and there's no lateral movement. Okay, that doesn't happen. So they're able to press this material with no lateral movement, no die edges. And so you can press really large shapes. Why can they do that? Because die fill is critical. They have to have in this die a uniform amount of material in this die to make this work. If they have more material on one end than another, the piece warps or cracks or whatever. Limited arrangement during pressing. Okay. Some issues with green strength are possible. Maybe you can use binders to take care of that. That's fine. But density gradients lead to shrinkage, and that's warping and cracking. Here's the cartoon version of an automated press. You have a shoe, okay, that provides material, fills the die. When this comes across, it pushes this piece out of the way, and then the bottom punch pulls down, creates a partial vacuum. Material flows in. When it pulls back across, it's ready, and then the top punch, which sits here, comes down and presses the part. Cycle happens again. Typically cam limited, also hydraulic. So you have mechanical and hydraulic. And I'm not going to discuss that today. And then they can make a shouldered piece. For example, this piece looks like this when it comes out, right, with a bottom piece on it. It's a shoulder with a hole, actually, through the middle. Okay, that's possible. Here's a compaction diagram, all right? This is the cartoon version. You have a log pressure, important, okay? Region 1, Region 2, Region 3. P1 is called the onset of granular deformation. You put your powder in, okay? And then the powder has a certain yield strength. That's your P1. So you compact the system. There's no change in density until you hit P1. And then this is your compaction cycle here in Region 2. Density goes up with increasing pressure on a log scale until it hits P2, okay? And P2 gives you your maximum density. If you exceed P2, then what happens is if you go up this curve to a higher pressure, okay, when you take the load off, it comes back down this curve to get to P2. So how do we get these values? Is that we measure them by measuring the deflection of the die, right? So you have a simple die set up like this with the punch on the top, right? And then your die out the bottom, and you measure this distance, and you calculate what your density is of your puck that's inside of this die. Okay, so when you unload, you get a springback defect. Springback defects can look like this, where you have, say, a cylinder, and you get what's called end capping. This piece flips off. I tell my students, go down to the grocery store or the Dollar General or something and get aspirin. And you look at aspirin, and aspirin are pressed pellets. And the cheap aspirin will delaminate, okay, into two pieces. And it's because they overpressed. So you get a crack down the middle, right? That's a delamination defect. You also would get this defect, which is called a slipstick defect, a lamination defect like this, that occurs on ejection. Because what happens in the die when you eject, right? If you have excessive pressure, the piece comes out, your pressed part sitting here, it's coming out, and when it gets to this point, it expands, okay? Because it's exaggerated, because what happens is you have so much stress in the system, it expands and it creates this system at this point. So the diameter expands out of the die. I know what you're gonna say. I think you said there was no lateral movement. Well, you get you create enough pressure to force the powder into the edges. There's not much movement, but there's pressure against the edge, right? And when you eject, you get a lamination defect. The other thing will happen is it will dome this end, okay? And that gives me either this defect or you get the lamination defect. So this defect gives you your cone, okay? And the other is, it gives you lamination defects. Humidity can play a role. This says granule density. That's incorrect, basically, because we're talking about, it's really no relationship to the granule. And this is the vibrating density, that's true, but you can see how linear this is at this point. And so you can extrapolate the linear of that line and this line to get your P1 value. They show that at low humidity, P1 increases. That's a plasticizing effect. But this springback is real. I ran across a group that isostatic pressing, which we're not going to talk about today, but they ended up with a bunch of data points out here, and they look like this. They were great because isostatic pressing has no die. And when they took it out, they thought the data was wrong. But when you get to a certain pressure, if you no longer have a die or whatever, you're going to come back to that above that pressure, you get the same density. So this point is real. So this was isostatic. It can still cause a springback defect. Okay, that brings us to spray drying. Spray drying is an agglomeration process from a slurry. You get much better mixing in a slurry than you get from any other technique. Each granule should be representative of the overall batch. So that means that each granule created in spray drying has the same composition. This is typically a narrow particle size distribution, arguably a normal distribution. It might be bimodal. The reason it's bimodal is that when the jet comes out of liquid, it starts to do this perturbations basically, and it will pinch off. And it pinches off into a little droplet and a big droplet, and a little droplet and a big droplet. This is called a satellite droplet, and it's this neck region here that forms this droplet. So you might get a bimodal distribution in spray drying. Okay. The spray dryer, a lot of these are cogeneration facilities, or are in certain places. So you get hot air from a turbine that comes in. This temperature going in can be around 700 degrees C. It's very hot. And it's fine because the hot air is coming in and going down. The slurry is being pumped in and spraying up. Okay. So it creates a droplet. You say, well, why don't I cook these at 700 C? It's because that droplet in this situation is evaporating moisture. Okay. And that evaporation of moisture cools the surface. So the spray dry droplet doesn't match the temperature of the spray dryer until all the water is gone. And as long as you have water left in the system, the droplet will be cooler than the conditions of the spray dryer. So you see that in this image, I go from 550 C down here down to 120 because I am evaporating moisture and sucking up that energy to reduce the temperature in the spray dryer. So this is a general configuration of a spray dryer at the bottom. I may have a slurry tank underground. It's not important. Ceramic suspension gets pumped in and is sprayed upwards, okay, like this. Some actually have jets that come in from the side and spray up. It doesn't make a difference. This is called a counter current spray dryer. The hot air in the system is coming down, okay? And it's being pulled into the system and then it goes out. The exhaust comes out this way, okay? Goes through a cyclone to pick up small particles. The particles get dropped out, no, both cases. Goes to a dust collector and then it goes out the exhaust. In Spain, in the tile industry, there's a place from the highway. You can see the plumes from 18 spray dryers operating 18 different factories making tile. This configuration that we see here, okay, and by the way, you can control the moisture content by the rate at which you inject spray. You can control it by the inlet temperature, but the outlet temperature is a response, not a variable. Okay, so T outlet is a response, meaning that if I increase my slurry in, I get a lower T outlet. If I if I decrease my and by the way, if I increase my slurry rate in, I get a lower T0 T outlet. I also get more moisture content in the granule coming out. So I can control that process by my inlet temperature, T inlet, okay, and my T outlet. By comparing those two, I can control the moisture content in the spray dry granule. Flowability. People in Spain have done a lot of work on spray drying in particular, but they find that if they're in this size range, and you recognize this as a cartoon, you know, from roughly 150 to 500 microns, they get good flowable granules. If they're below 100 microns, the fine particles make flow poor. And if they're above that point, they're getting satellite collection, meaning that big particles are moving and they collect smaller particles to make that particle irregular and doesn't flow well. This shape is interesting because that we call that the bagel, okay? And the bagel is because in the spray dryer, it shows in this cartoon version here, okay, you'll see this configuration, right? And the granule looks like this coming out. It comes in like this. But what happens is in the early stages of drying, it's hotter on the top than on the bottom. So this droplet in the spray dryer, okay, is warmer at top, hot, and cool, okay? So you get a thicker layer on the top of a dried material because it's drying quickly, and a thinner layer on the bottom with a liquid jelly center, if you will, and this ruptures, okay, to provide an opening. So that's what happens. And then you end up with this. They have multiple layers. I'm not sure about that. You only see it in the image. And by the way, this image implies cavitation, which is not true. It just so happened that this image here is a section across that. So you're looking, this is looking, wrong color, that direction, okay? And so if you cut it the right way, you'll get this image here. So if I cut this as is shown here, right, I get that image. So they would like to have this. Why do you get this? This is because they work with a dispersed suspension. You say, well, why does that cause this to happen? Dispersed suspensions then have the highest possible solids content, and they are the most desirable for spray drying because it requires the least amount of energy to spray dry the system then, because the evaporation of water costs a lot of money and it is difficult to do and expensive. So the way they get around the problem is they reduce then the water content by dispersing the system. That gives them donuts or bagels instead of granules. The way to do this is to reduce the water content and increase the salt content, okay, meaning soluble salts, to create a more compressible and deformable network, and you can get a uniform spray dry granule. What's the cost? Is the cost to evaporate water. So that's why it's not done that way. Okay, that brings us to cracking and warping, okay, and These are two sides of the same problem. Cracking is due to tension. Tension is pulling. Okay, so when I pull on something that's in tension, I press on it, it's compression. Warping is due to compression. So tension is due to pulling, of course, and that's cracking. Ceramics always fail in tension, always. If I bend the piece, it fails on the outward bend side. That's and 3-point bending, 4-point bending. Yesterday we talked about that. Warping is caused by compression. And what that means is that non-uniform particle packing in the body leads to differential shrinkage. So if I have a body and I have a region that's poorly packed, okay, so low density here, what happens is this wants to shrink more in the drying stages or in the firing stages, and that means that this is placed in tension, okay? And so correspondingly, the surrounding material is placed in compression, right? Because it's now being forced to try to compress. So you actually would draw it this way: compression radially, tension tangentially, or yeah, tangentially. Excuse me. Tangential compression, radial tension. So if I have a large difference in packing, then I would get cracking. If I have a small difference, I get warping. Here's the problem. We like to attribute cracking and warping to the drying process and to the firing or densification process, which I'm going to just call firing for sake of argument, okay? These are just where this occurs. It's not because of drying, and it's not because of firing. It's because of non-uniform packing in the green state of the system. Does that mean that I cannot create cracks in drying due to how fast I dry the material? No, but my potential to form cracks in drying are limited, and I've got to work pretty hard to do that. If that is due to the fact that I can evaporate water fast enough, because the evaporation of water creates capillary action that pulls the water from the interior to the exterior. So very fast evaporation of water can lead to locking the outside system. Similarly with firing. And my argument for firing is that when I do the firing situation, let's just take this as an example, okay? Let's say that I'm going to fire this tile that we just talked about, which is 2 meters by 3 meters. Okay, and I'm going to do that in a roller hearth kiln. My roller hearth kiln is, say, about 200 meters long, all right? And my time here, T0 to T final, is 50 minutes. Minutes, not hours, okay? My peak temperature is 1250 degrees C. My rollers are in here. They're, of course, much smaller and much closer together. My tile sits on here like this, and it's being propelled through this furnace. And so you could say I'm doing roughly 200 meters per hour, okay? The front end of this tile is going to be hot before the back end sees heat. When I center this piece, this thing is going to do this, and then it's going to do this, right? This part will densify and shrink. My shrinkage is about 16 to 20%. And it will do that shrinkage before the back end starts to shrink. So with this situation, and there's no other way around it, the thickness of this piece is typically on the order of 2 to 3 centimeters thick, okay? That piece will, this is going to be somewhere in here, right? And then by the time I get to here, this is my hot zone, if you will. By the time to get to here, this piece is now done shrinking. It's now its final, it's 2 to 3 millimeters, or meters, excuse me. Okay, so if I take 20% of this, this is actually about 3.6 meters large to start. This is about 2.4 meters large to start, and it gets to 2 meters and to 3 meters with firing. That piece deforms and shrinks one end before the other end is even hot. And we can't rectify that with the idea that I have firing problems that are associated with the material. That means that it is due to packing. I'm going to skip to here. Rim cracking. A lot of tension due to non-uniform packing. The density of the rim is less than the density of the well. I'm going to show you dinnerware pieces traditional ceramics because it's easy to generate these images. In this case, I have a uniform gradient from outside to inside, greatest gradient, lowest density on the exterior, and to the center. Here, in the center here, okay, I end up with a uniform density here. So the crack only extends to the foot and then it stops. I could calculate my density gradient based on the crack opening displacement. Okay. If I go to art as an art example, this piece cracked. There's actually soft edges. Doesn't look like it at the moment, but it's tension non-uniform, low tension in the rim. Okay. You say why? Well, they do a two-step process. The bisque firing process has no shrinkage, just drying. And then there's no shrinkage in bisque. Piece is hard. They glaze it. All their shrinkage occurs after glazing. Tend to work the bottom more than working the edge and the rim, and so it cracks that way. Okay. Oops. So center dropping, density of the rim is less than the density of the well. So as a clarification, this is the rim, right? This is the well. Okay. So the density of the rim is less than the well. That means that the density of the rim wants to shrink more. So you have a choice. What happens is in that case, the rim is now placed in compression. Excuse me, rim is placed in tension. Well is placed in compression. So when I have a well in compression, I have a plate like this, right? And then I go up to my edge. This has two places. If it's being pushed on, it can go up or it can go down. Gravity wins and it comes down like this, right? And then it warps down because of gravity is helping. So if I get to where the bottom of this is lower than the foot, I get what's called a spinner. Okay, so gravity wins and it goes down. If I fire it upside down, it would warp in the interior. Okay, so that means that a spinner is a pyroclastic deformation slumping problem, but it is assisted by a density difference in the system. Rim warping, opposite situation, density of the rim is greater than the density of the well. And so what happens is the rim wants to shrink less than the well. And so the rim is then placed in compression. And so in order to compensate for that compression, the rim will warp to handle that difference. So the distance it travels is longer than the point-to-point distance, and so it will warp. And how we know this is that we've taken these apart after the fact, and the density here and the density here are identical, which is another interesting part of sintering. In sintering, everything goes to the same density. So if you're low density to start, it has to shrink more. So your green density causes your shrinkage issues, okay? And then the density of the rim is greater than the density of the well. If it's sufficiently large, then you get a crack in the center. So where we are is here, and I'm going to ignore this for the moment in the efforts of time. I think what I'll do is I'll pick up with particle packing tomorrow because we're at 11 o'clock. And what I'll do is I'll get through particle packing and I'll get through thermal processes tomorrow. We'll talk a little bit about statistics and we'll call it a course. So I'm going to stop sharing. We will start here tomorrow with particle packing. We covered a lot of material today. I really do welcome questions if there are any questions. You are very silent, of course. But if you have questions for me, please forward them on. You can email them to me also. And then we'll be back tomorrow morning, 9 a.m. Comments, questions? We good?